All right, hello everyone. It is 3 minutes after the hour. We are starting on MIT time, a couple minutes late. It is wonderful to have Sven Krippendorf giving an IAIFI colloquium today. Sven is a senior researcher at LMU Munich. Sven and his team are focusing their research these days at the interface of physics and machine learning, which makes it rather relevant for us. Tackling questions on a wide variety of topics in astrophysics, cosmology, and mathematical physics. He is a member of the Erisita collaboration and involved in the Athena mission, both of which are X-ray observatories, and also has a significant body of work in particle astrophysics and string theory. Most of his ML work is concerned with how to utilize ML in aspects of theoretical physics that are traditionally driven by careful thought rather than difficult computer computations, such as identifying the symmetries of physical systems. Today, he will talk about his work on finding and utilizing functional biases in theoretical physics. And Sven, it is a delight to have you here. So please take it away.
Yeah, thank you very much, Jim. And yeah, thank you very much for the invitation to talk about our work at the interface of theoretical physics and machine learning. So to start discussing this, I think, new connections between theoretical physics and machine learning, let me begin with the theoretical physics perspective and start with this quote by Steven Weinberg. Our purpose in theoretical physics is not to describe the world as we find it, but to explain in the terms of a few fundamental principles why the world is the way it is. And for me, a really tantalizing question is, to which level can modern machine learning achieve, this what we do as theoretical physicists? And if the machines can actually achieve this, I think a really interesting question is, which new physics can be revealed with such methods? And today, the plan is to first talk about an example of where we can use machine learning to get better insights into physics, and particular into a long-standing problem of finding metrics relevant in string theory, so-called Calabi-Yau metrics. And I discussed this example because it highlights a feature which we see across various domains when applying machine learning to physical problems. And this is that we are required to use our domain knowledge to bias the respective machine learning answers. So this is just basically as an example of what appears in a lot of other fields. And then in the second part, I then want to move to the question of, how can we deal with situations when we do not know this domain knowledge and these respective functional biases. So how can we use machine learning to address this? For instance, I'll discuss how can we search for the symmetries of a system. And all of these problems have very much in common that they require searching in high-dimensional data spaces. And this is where I think machine learning becomes a key player to tackle all of these problems. And why is that? Well, a lot of recent advances in machine learning are really examples where standard cursors of dimensionality can be overcome. And the interesting aspect of this whole story is that this can really be understood of implementing efficient functional biases into feed-forward neural networks, in particular to equip them with appropriate symmetries. For instance, the classic example that we all know is that of translation symmetry, which is heavily used in convolutional neural networks these days. And this clearly goes beyond and is realized in various aspects in the beautiful field of geometric deep learning. But such functional biases, in particular symmetries, provide also a very tight connection with physics, where we in a standard way use and develop these structures. So I think this is really exciting to see the successes on our physics questions with ML being actually down to applying standard structures we've already used in physics a lot of the time. And so that's very cool. So I'd like to highlight for this work, this is done in collaboration with a lot of excellent collaborators, and it's a pleasure to work with them. So the first part is based on work together with Laura Anderson, James Gray, Nikhil Raghuram, all at Virginia Tech. Fabian Rühle, who is recently moved to Northeastern, and Mathis Gerdes, who was my master student and is now pursuing his PhD in Amsterdam. The second part is about work with local people here in Munich. So Philipp Betzler, Mark Sivery, who recently graduated, and Dieter List. Okay, let's get started with this example of how we can search for metrics with machine learning. Should also flag that beyond our work, around the same time, two other groups, by Mike Douglas and Vishnu Chijala, also had work in along similar directions. And by now there are several other groups also following this. Okay, so why am I talking about the metric as a theoretical physicist? Well, if I'm thinking about extra-dimensional physics models, I can't get around the metric. The metric is immediately there when I write down the action. If I look at the Einstein-Hilbert action, I see that this really depends on the metric, and the extra-dimensional metric appears there immediately. So that's an object I really need to understand in order to talk about the low energy effective action very much. And you can make phenomenological properties very explicit, but let's stay with the very big picture of why, as a string theorist, I'm very much interested in understanding the effective action. Why am I driven? What physics question is behind this? And this is basically to somehow get an angle at the question how to distinguish the effective field theories that arise in string theory from ordinary BSM models that I can write down. So in the sense of, why, what makes these theories special? What would be phenomenological properties that I can search for? Good. And so this is why I'm interested in metrics. Now, we can also be in string theory very precise about which metrics we are very interested in looking for. And this is basically pretty clear that one really canonical example to look for is so-called Calabi-Yau manifolds. And these are manifolds which have a Ricci flat Kähler metric. So these are spaces which have a metric with very special properties. And from the mathematics side, we know the existence of such metrics. And that's obviously, we know also that they're unique. However, an explicit construction, even numerical, is very hard. And so this is something that has been bothering people for a very long time. Now, there are various ways of defining Calabi-Yau manifolds. Here's one, just to write down a definition, which is very useful for us in the following. And basically that is, we are interested in complex threefolds, which admit a nowhere vanishing real two form J, and a complex three form omega, such that the following conditions are satisfied. Yeah. Obviously, we don't need to remember all of those, but basically we can have very precise conditions on these forms that we need to satisfy. Now, the metric itself is stuck in the J, effectively. Yeah, so components are effectively, I say, in that two form J. And the simplest example that you can think of Calabi-Yau manifolds are hypersurfaces in projective spaces. The simplest example is that of complex projective four-dimensional CP4, and you look at the hypersurface in these spaces. So you'll have an equation which you have to satisfy. So that hypersurface in P4, that's what we are interested in. And from that hypersurface equation, you can construct omega very easily, but G, or respectively J, is the one that we're interested in. Now, the question then is, okay, which kind of metrics should we look for? Which metrics should we write down? And this is really, we can write down an ansatz for metrics relatively easily. In particular, we can take the Fubini study metric from the ambient space and pull it back to that surface. However, such a metric would not be Ricci flat. Yeah, so we are interested in finding other metrics on these spaces which are Ricci flat. Now, the ansatz, and this is where the kind of bias starts to enter the discussion, is when we look at a particular ansatz that people have come across, which is very fruitful in this in writing down, looking for metrics. And this is that of the so-called generalized Fubini study metrics. And what one starts off is not with the metric, but a scalar valued function, often referred to as the Kähler potential K, from which one can deduce the metric by taking twice the derivative. Now, that reduces effectively the components. Now, what function K does one choose? Well, it's a generalized Fubini study metric, so it still has the same logarithmic structure, but what is written in the logarithm is slightly changed. And it's changed in such a way that the coordinates appear here in terms of polynomials, and that there is some matrix H which is multiplying the two together effectively. And in this capital H in this ansatz, this is exactly the parameters or the matrix we effectively want to learn in a very biased ansatz. Okay. Now, the sum here, as this is kind of the level of, is telling you which degree of polynomials I'm taking in this ansatz. And you can think about this, about the accuracy, kind of how many, how high a resolution effectively you want to go. The higher you go in terms of polynomials that you allow to, the higher the accuracy gets. Now, let me kind of give an overview of why am I talking about this, and why do I say, okay, this is a hard problem, because analytic solutions are not known for the compact threefold cases, but people have obviously tried numerical approaches. And so the most successful ones prior to ML work were those based on spectral methods. And they actually, can work, but they work rather inefficiently. So what effectively happens is that you can use those methods to calculate the metric at a single point in moduli space. So for, whereas we are interested in, knowing the metric, how it depends on sizes of extra dimensions, how shapes of extra dimensions. And these and the second downside of these methods is that high accuracies become rather expensive numerically. On a conceptual side, the ansatz here is rather limited in the sense that it only allows for Kähler solutions. And so more general string theory backgrounds are not covered with these methods. So to put it short, what am I aiming at? I'm aiming at, having tools that can get me the metric at a reasonable speed, so I can do phenomenology with those. Reasonable speed meaning that I can, if I let something run for a day or so, that I can get a reasonable metric. Okay. And that clearly is not possible at high accuracy with these spectral methods. So the question we were after is, okay, can we formulate this? Can we use machine learning to actually get metrics in this? And so to formulate it as suitable for machine learning, I have to formulate this problem of finding metrics as an appropriate optimization problem. And how does this work? Well, so first of all, we have various conditions that our metric has to satisfy, and we formulate them as loss functions. So the first one being that our metric has to be Ricci flat. So I can, calculate the Ricci tensor from the metric if I want to. However, this requires effectively a lot of derivatives. So there are other ways which turn out to be computationally more efficient, which we resort to in this context, which is looking at balancing these two forms, omega and j, appropriately. And you can do this via an equation which is referred to as a Monge-Ampere equation. So basically, you can formulate it as such a condition, and this can be formulated as a loss function as such. The second condition that has to be satisfied is that your metric should be scalar. So that the condition, the j has to be equal to 0. Again, on a component level, this can be formulated as a loss function that you have to that your solution has to satisfy. And finally, we are talking about various coordinate patches, so the transition functions have to be satisfied as well. Okay. Now, let me give an overview on the experiments that we are working on, or that we have presented. So we got various things to work. The first thing we tried was to look at supervised learning of the scalar potential. So we run effectively data, so we trained with data from running those spectral algorithms. And then basically we got good interpolation between such points from using a machine learning approach. But then we switched gears a little bit and went to just using these loss functions to optimize for the scalar potential directly. And that really shortcuts completely using these spectral methods at all. And then to address the conceptual level in order to go for more general metrics, we also looked at learning the metric in an unsupervised way directly. Again, in order to get those to work, what we really had to do is we had to start from a very good starting point, effectively, and then perturb from there. And that was basically making an ansatz, which is just a perturbation to the Fubini study metric. And then we actually use such metrics to look for metrics in a more general class, namely SU3 structure manifolds. Okay, let me show you some results from one of these unsupervised experiments. So what we did is basically we are interested in learning this matrix H effectively, right? That's the matrix H. Well, this matrix H should depend on the shape modulus, so this psi parameter that appeared in the defining equation. So that's the input to our network. Now we can combine, once we have H, together with points sampled from that space to get K and respectively G directly. Now and then we let the machine run with this effectively, and here are some results where we do a spectral resolution with K equal to 6. So this corresponds to a matrix which has roughly 40,000 components. So this is the kind of resolution that we are looking at here. And in green, I'm showing you the results for spectral methods, namely so-called Donaldson's algorithm when we let it run. And in blue and orange, respectively, are our networks that we've trained in a regime between 10 and 100, shown here. And clearly in that regime, we are getting much more accurate results. However, this also persists when we go into the regime where we haven't trained. So for a regime, for reasonable values, we are still better in regimes where the network really learns how the metric should behave, at least for some parts of it. So here in dashed, this is the extrapolation. If I were to just use that point, and I'm still over a far range of values, much better. So that's, I think, very nice. Now, let me also highlight a little bit the our work when we look beyond Calabi-Yau metrics. So what effectively has to be done is that our loss functions just have to be modified slightly. Yeah, so we had, for instance, a condition dj being 0. Now, what effectively happens is that this gets modified to something which looks like this. And again, in this example with SU3 structure, we can modify our loss functions, and we can learn the metric again appropriately. As a kind of summary of these, how our methods compare with these previous numerical approaches, is basically shown in this table. So all methods work very nicely, or work at fixed points in the moduli space, or at fixed parameters. However, when we're looking at moduli dependence, our scalar potential learning and metric learning really have an advantage over the previous methods. Now, if we're looking at methods for looking at non-scalar metrics, only our metric methods are actually applicable in terms of numerics. Now, it's always good to see where this is heading, and what we would like as well at some point is that these methods are obviously numerical approximations, and as theorists, we would like to also see analytic results. And so this is, I think, a perfect place for anybody in formula fitting to try to find interesting analytic approximations. This story about using neural networks to find solutions to PDEs is not an only example here in terms of solving Einstein's equation. This is something which appears across various domains. And so I'm just listing a couple of examples. And it seems to be a universal, or relatively, applied in relatively different areas that machine learning can actually help to solve PDEs. So this is, I think, Calabi-Yau metrics are no exception in this story. Now, having seen that we, need to have, such a, scalar potential ansatz, or we have to know kind of what a good perturbation is to, what a good starting point is to look for those metrics. I think this is, often the case, and but we are also often in situations where, where we do not have such a domain knowledge, or where it would be very hard to do this. And this is something, this domain knowledge, has been obtained with humans working for decades effectively to understand these structures that have to be there. And so the question is, can we actually use AI also to identify such a domain knowledge and, automatize this process as well. Now, this, identifying such mathematical or physical structures is the question I want to talk about in the second part of this talk. And in this context, I would like to also, highlight the work also done at IAIFI in this context by Max Tegmark and his group, who has been also pursuing relatively similar questions in this direction. Okay, so let's put this a little bit into context to see where does this fit in. So this similar questions you can ask in different fields. So if you were to put yourself into the situation of looking into chemistry pre-1869, you would be interested in finding underlying structures to order the chemical elements. And this would require you, for instance, to identify the periodic table. And again, this is something you could ask whether the machine can do this. And these people have effectively done this. Turning into particle physics, the story goes back to the 60s, 70s, etc., when our standard model of particle physics has been developed, and a very similar question would be, would have been, to actually detect these mathematical structures that we now know can write on the mug of coffee. So the question that has been bothering me or is bothering me is which tools do we actually need to make such discoveries with ML in the 2020s? And for me, this is overall the scheme is to be able to find mathematical structures to describe systems more efficiently. And this is across domains, I think, and you can ask this from really various directions. You can ask this in terms of astrophysics when you're talking about, how do you get your favorite dark matter profile? How do you look at strongly coupled systems? What's if effective field theory? What are the efficient ways of describing strongly coupled systems? But also when I'm talking about data sets arising in string theory or particular properties of string theory. And so our approach has been basically to search for structures that we know in theoretical physics that have been developed, and to develop tools that can do this. In particular, I'll talk about how to search for symmetries, how to search for dualities, and how to search for integrability in this context. If you're coming from a machine learning based background, the idea you are probably very familiar with that symmetry is a very useful tool, by now. But all these other tools about dualities and integrability are further physics tools that are also very interesting in terms of having efficient parameter inference and predictions. So there are other ways of having good functional biases. So let me get started with the first work is on how can we identify symmetries, and here in the context from looking at embedding layers. So, one second. Okay, so how do we search for the symmetries? So the first, so what's the problem that we are facing? So the simplest example, if we are thinking about symmetries, is we're thinking about a Higgs-like potential in the first instance. And what we're interested in is to find what are the invariances and then what symmetry lies beyond such invariances. So if I place this into just looking at the radial coordinate, this picture becomes looking like something like this. So the question that we're interested in is, how do we find these invariances that group all of these points together and that identify all of these points together and these points together? So we need a method that can group the input with the same meaning together. And it turns out that this can be achieved by carefully looking at the embedding layer neural networks do find very deep in the network. So you start with some, you coordinate input X and Y, and you want to classify in this neural network just, which potential value you have in these classes. And by doing such a simple task, you can look at then what the network has learned, where does it fit, where does it put all of these points here. So this is something, the idea behind this is that neural networks will group things together with similar meaning. And this is something which obviously appeared in machine learning before. When you're looking at word embeddings, for instance, relatively deep in networks. So if you're looking at word to vector, if you're looking at word embeddings very relatively deep, you would group points, or you would group words with similar meanings close together in that space. And so what we wanted to ask is whether we can see my slide is so can we search? So the question we wanted to ask is, can we search for symmetries exactly in this way? And the answer to this question is yes. So what we looked at here, for instance, in the sixth case, is what is the embedding that we are finding. And now when you look at the dimensional reduction, you can really see a cluster separation. That's one way of looking at it. You can also look at the distances directly in that high dimensional space, but visually you can also see that these are being clustered together. Now, this is only part of the story, because obviously what we want to do is, once we have identified such an invariant, such a cluster of points, which in the input space look then like some point cloud, what is the underlying symmetry associated to these points? And basically, what we use is that we look at close neighboring points and see how they are connected. Now, you have to be careful how to set up your regression problem in order to determine all of the components. But when you do this, you end up with the dominant generators for these point cloud. And so in this example, this is exactly the SO2 generator that you very much know. Now you can do this example for more sophisticated cases, namely here looking at SO4, SU2, or SO3. And you can pursue exactly the same story and identify the generators associated to those. And you can go to relatively sparse points as well, so that's working quite nicely. Now, this is not always the same way of how you want to search for symmetries. There's another story to how to search for those. And this is from basically another way that how we can search for those is by looking directly at just samples of phase space. So what's the story here? So this brings me back to 2016. So the work by Battaglia et al. And various other groups, where the goal is to predict the future time steps of a system that you're seeing. Now, in this context, we are looking at not at the high dimensional input, but we're looking at the dimensionally reduced and pre-processed input in terms of that it's nicely given in terms of phase space variables. So effectively, you're given P and Q, and your task is to predict the next time step of these points. Now, you can try to do this by basically starting with a standard feed-forward neural network and predict P dot and Q dot. Now, this is shown here for a two-body system, a gravitational two-body system. And you see that the predictions that you're actually getting are not very accurate. However, and this brings me to 2019, the story of Gridanos et al., and that of Hamiltonian neural networks, where it is much more efficient to actually not predict P dot and Q dot directly, but rather to predict the Hamiltonian of the system, and then to use auto-differentiation to predict P dot and Q dot. And so what this does is effectively it puts the bias on that we want to enforce energy conservation. And so what happens is, when you look at the system here, in this case, the dynamics are significantly improved. Now, the question we asked is, can we actually learn more structure from samples of phase space? So not just the Hamiltonian, but other properties of the system. In particular, can we learn the symmetries of the system? So, for instance, we know in Hamiltonian dynamics that whenever we have a conserved quantity, that the coordinate associated to those are cyclic. And so we really know mathematical conditions on such coordinates that we can impose. Now, when we do this, now if we know the condition, what we have to do is effectively, we have to formulate our search problem as an optimization problem, right? So we have to put this into loss functions again, and then start with appropriate architectures to learn those. And then we're interested in two questions. So the first one being, okay, say this learns conserved quantities, then can we extract those as well? And can we extract those analytically as well? Can we understand those? Now, this is some, simple formula fitting that we have to do. And the second one is also when we learn these symmetries, can we actually also improve upon the dynamics that we get with Hamiltonian neural networks? So if we put additional bias on. So what's our system? What's our network then? It's basically the following kind of setup, that we are learning, first of all, appropriate coordinate transformation, which reveals the conserved quantities. So we are going to different coordinates P and Q. Only a subset obviously then has to enter into our second network, the Hamiltonian network. And the loss functions that we have to then do have to be, you have to sit down and calculate them. But the basic thing that the basic thing that goes into this whole story is that that it is this kind of observation that the Poisson bracket, that the Poisson bracket with the Hamiltonian of such a quantity has to vanish. Right? So any conserved quantity has a Poisson bracket with the Hamiltonian which has to vanish. And effectively, what this does is it reduces the space where it can move. Yeah, so it basically, motion is just taking place on a hypersurface in phase space. Now, okay, as you can see, the results here are so these are then the equations. You still have to satisfy Hamilton's equation. You still have to have consistency conditions on the coordinates that you have to satisfy. And these are all implemented as additional loss terms. Now, when you do this story in terms of trajectories, you get very nice results. Now, when we're looking at then these two goals that we had in mind, so one is to then open the box and see, okay, which quantities have we actually learned, right? So which quantities are in this intermediate output which are presented, then you can see that this is really a linear combination of this total momentum components and angular momentum. Yeah, and that's really, I think, nice, that the standard thing that we would expect actually comes out. Then the other thing that we can see, if we look at how the deviations of these trajectories are and how the conservation is going, this actually improved in terms of these by using our constrained neural networks. Now, this is a very nice toy example, but this is not really, the two-body problem does not reveal us any new kind of symmetries. This is not something, it's a very starting point. So then the next step is to actually switch gears and see, okay, where can we take this in order to get some new insights? And so this is this work on where we try to look for basically integrability of systems and gear up for technology with this. A lightning overview of integrability is the following, just to set the theme. So basically, a system is integrable if and only if there are n independent, everywhere differentiable integrals of motion, which are also in involution. So basically, your system is completely constrained. Yeah, you have effectively just integrals of motion, and then your system dynamics are completely constrained. Now, this is potentially a very hard thing to search for if you're thinking about field theories, because that would mean that you would have to look for infinitely infinite number of conserved quantities. So there are clever ways of formulating this and searching for structures to actually show that a system is integrable. And this is by searching for a Lux pair or respectively a Lux connection in the context of field theories. So what is this? This is effectively a matrix valued equation or matrices L and M, which satisfy this equation. And then the conserved quantities are revealed as such that you take the power of these matrices L to the K and take the trace of those. Let's put this into a very simple example. Take the harmonic oscillator and look at standard Hamiltonian and equations of motion. So a Lux pair for this condition would be this one, which is shown here. And now from this, let me move this slightly. Okay. So from this, you can see then from this L, you can deduce the conserved quantity. So in this case, it's rather boring because it's effectively just the Hamiltonian that you see that is appearing here. But this is just to keep a very simple example to make it very, very clear. Now, why am I talking about integrability? Because integrability is a very powerful tool which analyzes a lot of systems. So in particular, one thing to highlight is there are lots of very interesting structures in n equals to 4 super Yang-Mills theory, in particular in the planar limit, where integrability is forcing you a lot of very interesting structures. So, and it goes across domains obviously where things are. So now to set the scene a little bit here and why machine learning I think is very helpful in this regard, let me quote Nicholas Beisert's lectures on integrability here, where he comments about a Lux pair. And so he calls having a Lux pair very convenient. As I hope I've illustrated, that this looks nice, but it's very much inspiration is needed to find it. And it's hardly transparent, its structure is hardly transparent. And so he concludes or writes, the concept of a Lux pair does not provide, decide whether a system, any given system is integral, unless one is very lucky to find a sufficiently large Lux pair, right? So this sounds like a really good search problem, which obviously, humans have sat down and constructed Lux pairs over decades. But we wanted to ask, okay, can we actually, let the machine search for these Lux pairs and find them for us? And that's a story that we did in this paper. So again, we started out setting out the machinery. So effectively, we want to find these new Lux pairs, obviously in an unsupervised way. So we don't want to require any knowledge about the Lux pair beforehand. So the optimization problem that we have to solve is the following. So we have to find matrices L and M, which satisfy this equation. So we can put this into a loss, relatively simple. But then it starts to get a little bit more tricky because there are further conditions in the sense that this has to be equivalent to the equations of motion. So then the equations of motion typically take such a form, right? You can write them as x dot and then some function which depends on the variables and this derivatives respectively. So what we set up is effectively when you look at a lot of Lux pairs is a system, is a loss function where x is somewhere included in L. Any of these coordinates is somewhere included in L. And respectively, the right-hand side of the equations of motions is f is included in the commutator of L and M. Now, why are they such horrible expressions? It's basically because you have to take into account, so this can be in any component, but also it can be proportional to these equations of motion, right? So that's something that your loss function has to account for. And that's done with these combinations. Now, this is not enough. What it acquires as well is, a lot of the time, you're always in danger to finding just zeros, effectively, that your network is trying to collapse because this equation if you would just put zeros everywhere, would be satisfied. So what you in addition have to include is something which ensures that no mode collapse is happening. So overall, you end up with this loss, these loss components. So the Lux component, this equation of motion constraint, and this mode collapse. And then you can make an appropriate ansatz for your network. And again, just to highlight, as an example, with a simple example with a harmonic oscillator, you can run your network, and you can effectively, get out L's and M's. You can check that the equations of motions are actually, satisfied, and you can look at the conserved quantities. Now, the harmonic oscillator itself is just, a little bit boring, obviously. So we pushed a bit further and looked at standard other integrable systems. So we looked at KdV. So this is waves and shallow water, respectively, where you have an equation of motion which looks like this. We looked at the Heisenberg magnet, and we looked at nonlinear O and nonlinear sigma models, in particular the Sine-Gordon equation and the principal chiral model. So we all get these to work. Now, another aspect to integrable systems is the fact that if we know that a certain system is integrable, one is often interested in to see whether if I add a perturbation to this system, so I'm adding another term in the Hamiltonian, for instance, something like this or something like this, whether the system actually remains integrable or not. So, and here again, this is something which we can address with machine learning. So what we do is we effectively initialize the network at the solution for the unperturbed system, and then see how it reacts to samples from a perturbed system. And you can see that in the case of this integrable perturbation in the 2D harmonic oscillator, it relaxes to a new solution, and it's respectively the loss is very low. Whereas for the non-integrable perturbation, you really see a numerical difference. So this is, I think, a numerical route to search for such perturbations. Okay, let me see how I'm use time. Good. Good. So now, having looked at integrability, and I think that's something we can push forward now. But in the rest of the talk, I want to talk about another theoretical physics approach where we can look for structure, and that is that story of dualities. And this is a structure which is not really directly implemented. Unlike symmetries, this is not something which, to my knowledge, is pushed into machine learning architectures very much, at least knowingly not. So this is something which appears across physics in various disguises, ranging from the classic example of the 2D Ising model, where you have a self-duality between the low and high temperature phases, to holography, to field theories, and obviously also in the context of string theory. Now, in essence, what are dualities and what are they useful for? So in essence, we are faced with different descriptions of the system. So they are in different variables and potentially also on different background spaces. So there are two different descriptions, but they lead to the same correlation functions. Now, to illustrate this a little bit, let me give you a very simple example of, where you have some noise and you put, just some signal in momentum space, and you just want to distinguish situations, such situations. Now, if I were to transform this to position space, you would smear out that signal completely into every frequency bin. So if by eye you look at these two spectra, you would have no clue at first hand whether there is something. Whereas if I look at these in momentum space, this becomes relatively clear. Now, you can put this in terms of physical systems as well. So for instance, if you're asking the question of which temperature sample something is drawn from in the 2D Ising model, this is something you can much easier answer in a high temperature phase than in a low temperature phase. So this is something, the story is that, certain correlation functions are easier to evaluate in one description of the system than the other. And that can vary obviously between different correlation functions and which state of the system you're looking at. Now, the question we wanted to ask then in this work is, does a neural network actually use such transformations automatically? And so, for instance, does it use a discrete Fourier transformation in the example that I was showing earlier with these, to distinguish between signal and noise? And the answer to this is no. So if you're starting from some random starting point with your neural network, it will not converge to such a solution. Now, if the answer to this is, if we cannot, if it does not find such a good solution, can we maybe enforce it? Yeah? Can we drive the network to learn such good representations? And how can we make this? We can make by effectively adding additional loss terms. And what we experimented with various things in various contexts. So in case of this Fourier example, what worked was to maximize the distance between signal and noise effectively. So this is an adaptation of triplet loss effectively that we are using here. And what this effectively does, it assists you in this kind of cartoon picture to drive to a good solution. So when you're looking at now these learned representations, and by applying this additional loss and compare it with the features that you've put in, there's really a very good correlation between those. And if you see, then it picks out obviously them at various orders, so various positions, but that doesn't matter. You can see that it predominantly picks two features, and this very much is resemblant of the Fourier transformation that you know as a very good solution. Now we put this into very simple toy examples in physics, and basically looking at again spin interactions. So 1D Ising, simple 1D Ising model with spin interaction, multiple spin interactions, and there it depends on which variable you use effectively. And there are again certain properties which are much easier in one variable to determine versus the other. And the question was, okay, how can we force the system again to obey such good representation? And what worked here was to use kind of an autoencoder setup where on the latent dimension we put an additional loss when we train the autoencoder, mainly that it is good at doing some intermediate hard task effectively. Yeah, so it's kind of a pre-training where we are looking at learning somehow this good these variables, and once we do this, then we actually can do much harder tasks more efficiently with this pre-trained network. And what I find exciting is, again, if you look at these latent variables, they again, in some cases, rather close to these actual variables. So that's a nice way, at least in these simple systems, to see good variables appear. Now let me conclude the talk. So what I've convinced you about and shown you is that biasing networks with physics knowledge is a very good thing to do, and that this can lead to rather efficient results. So in particular, if we're looking at our biased networks to look for numerical Calabi-Yau metrics, we can really use them to do good science, find new metrics. But this is also something where we can use mathematical structures such as symmetries, symmetry constraints to improve simulations. Then in the second part of the talk, I hopefully demonstrated that in these cases, finding the bias is also possible. So we can learn mathematical structures, the Hamiltonian, the symmetries. We can learn those in an unsupervised way. And the condition to do this is really that we have appropriate loss functions can be identified. So I showed you two examples, one being those symmetries from the learning them from the embedding layer, but also learning these symmetries from phase-space samples. Now, the last point, allows us then to actually also look in a very similar way to set up a machinery, which I think, has the potential for discovering novel structures in integrability. And so what we've set up is to look for Lux pairs and Lux connections for classical systems, and within this machinery also to identify integrable perturbations. So, and finally, what I find very interesting is that in terms of dualities, it's possible to see some interpretation when we and structure appearing in these latent variables when we enforce certain losses, and we can identify them as variables of a dual theory. And I think that's again a very nice principal discovery tool for finding new descriptions of dynamical systems and understanding those. So with that, I would like to thank you for tuning in, and I'm very happy to hear any questions and to discuss anything further. Thank you very much.
Sven, thank you very much. That was a wonderful colloquium on a number of things. It was great to hear everything well, not everything, many of the things that you are doing and that your group is doing. I'm sure there are a handful of questions. If anyone has a question, please just raise your hand and we will unmute you. Anandita.
Thank you for the beautiful talk. My question is from the first half, where you have used unsupervised learning to learn Calabi-Yau metric. What are the exact opted policy and actions and state space that you have used? And I was wondering if you could use generative networks to make better predictions.
Okay. So you're asking, so let me, okay, so in this part, so you're asking about assumptions about our size. Is that what you're asking about? Okay, good. So in terms of this size here, what we do is we effectively, we want to learn the metric, right? The psi dependence of that metric, or metric with various psi values. Now, what we've done is basically, we have to fix a certain range. Well, we see that this is working nicely if we fix a certain range. So we've done this for various ranges. Here I'm showing from 10 to 100. We have other examples in the paper. And really, I think our policy behind this is basically try something that seems a reasonable range. Yeah, I mean, and to see where things are starting. As you can see, right, we have this up to 100 here. Like, there's really one thing that needs to be developed much further. Is to make sure that you can do this over really the entire range, and pushing these ranges much further. Right, we really see performance differences appearing, right, when we increase this. That's a natural thing, because it's not yet the perfect metric that these networks have converged to. But
that makes sense.
Yes. Does this address your question, or maybe I missed some parts of your question?
It does. I was wondering if generative adversarial networks or any kind of oracle can work well.
Yes. Okay. Good. Yes. Yeah. Yeah. Thanks a lot. So generative networks. Yeah, this is obviously a very interesting, aspect. At this level, what you would hope for is potentially at some point, right? You can, guess things much faster. If you're talking about guessing metrics, for instance, for various background metrics, backgrounds, and so on, and to reutilize structure that you've seen from one and one Calabi-Yau to put it to the next. That's something which is very reasonable because we have same local structures, say the PETSO devices and so on, appearing in various things. So locally, certain things will look the same. Yeah, it's a future thing, and I think that's all I can say right now on this.
All right. Thank you for explaining.
We have a question from Arton, who is also an expert on Calabi-Yaus. So.
Thanks, James. Yes, it was a very good talk. Thank you for that. I just have a very naive question, rather. So you mentioned the super Yang-Mills theories and theories similar to that. So sometimes, to my understanding, sometimes the symmetry of these theories could be some kind of categorical symmetry. So you have these equations, and there is a certain, I think it's certain symmetries can be induced on the space of solutions to differential equations that govern dynamics of your system. And these symmetries are induced by the underlying gauge symmetry in the original system. However, you can only measure them when you look at the space that parameterizes solutions to these equations. So in terms of machine learning, I'm very interested to see how would you investigate those kind of symmetries. For instance, I think in the string theory, since you mentioned it already, for instance, there is S-duality, right? So S-duality has many consequences. One of them is in the level of the space of solutions to differential equations that govern these theories. S-duality, for instance, can induce symmetries in the space or symmetries in the even counting of solutions to those equations. When you perturb the parameters, let's say.
Could you get to your question, if you don't mind?
Yeah. So
Yeah,
the question is that when you want to measure your symmetries, it seems like you are able to work on phase space, and it seems like you don't have a coordinate-free description. You always need to set the coordinates on your phase space, but many of these symmetries are defined on spaces that you cannot even have local coordinates. So how do you do that if, let's say, you want to persuade some symmetry in certain theory? Your space could be so bad that you just cannot have a coordinate description of it locally to investigate these differential equations. What would you do there?
Okay, good. So there are lots of different aspects on how to extend it. But the bottom line is that you will always have some dynamical system, right, that you somehow have to have access to. And the access to that we actually need here are just points in phase space. So in order for any of your analysis to work, you have to have certain access to your system. And I think the one of the key things in this, for instance, in the integrability story, where this appears, let me put up something like this, is literally this one here, is literally, right, what we really don't need is closed form solutions or things like this, yeah, for these differential equations. We're literally just looking at single points. And so this is, I think, a very minimal approach that we need. Whether this addresses completely, all cases that you have in mind, I don't know. However, I think what you have to have some way of phrasing your question effectively, right? So you have to have some handle on your system. And in general, I think you can work on making this as as a adaptive to your problem. So if you don't want to talk about phase space samples, but about some other input, the crucial bit is to be able to formulate it as an optimization problem. As soon as you can do that, I think, you can search for such structures.
I see. So I gather that you need at least some level of smoothness over the spaces that you're working on, or at least at this point, you don't have coordinate-free description of or way of approaching these problems.
Not right now, but I also have not thought about this too deeply. There's a lot of stuff that can be covered for such systems.
I see. Okay.
All right. Are there other questions out there? While they come up, maybe I'll ask one quickly. In this integrability story, you were deforming the harmonic oscillator. Are the deformations of the harmonic oscillator that are integrable classified? I mean, I noticed that the quadratic deformation was integrable in ML and the quartic was not. I guess that wasn't totally surprising, perhaps. What's known about this?
Yes, so that's a very good story. So I don't know the exact answer to your question, but if you're thinking about things like TT bar, etc., this is the whole story when people think about perturbations of systems. So again, I think it's generally not known which perturbations are integrable. And so this is effectively, I think, now I think you have a hammer effectively where you can try writing down any effective field theory operator you can possibly think of, and applying this hammer to it and see whether the system remains integrable or not.
It's great that you guys did it, regardless of whether or not it's known. And I hear you about the hammer. I mean, did you try a linear deformation by any chance? I would expect that to maybe be integrable as well.
Yes, I think so. But I mean, we didn't put it in.
Other questions out there for Sven?
I have a question. For learning the symmetries and the Hamiltonian in the phase space, I was wondering, how have you defined the object policy and the actions and the state space and the environment for the neural network to learn something so theoretical like the Hamiltonian, which is an expression, a closed form expression?
And indeed, to clarify, it's not reinforcement learning. You're using reinforcement learning language. But...
Oh yeah, sorry about that. But I was wondering that how the neural network learns the expression of Hamiltonian, starting with just data from dynamics.
Yes, yeah, thanks a lot. So I can, so effectively, right, what you have to set up in this, what you have to specify is a number of conserved quantities effectively that you want to enforce in the symmetry control neural networks. So you can search for one conserved quantity, 2, 3, 4. That's why I was showing on the next slide results with, varying numbers of conserved quantities, so networks that have various numbers of conserved quantities. That's a setup that you have to put in, and that's effectively determining all the loss terms effectively that you have to put in. Now, how do you find? So this is obviously a neural network output, right? That you get. How do you get to those formulae effectively? Is basically by doing appropriate formula fitting to that neural network output. So this is the same approach as done by Shirley Ho and her group when they look for finding analytic formulae to something a neural network has learned. What we are doing here is, because it's very simple, we can just restrict ourselves to polynomials and see what the best fits are, and that works very nicely. The story why you do it in this kind of order is basically that the search problem becomes much more tractable in this order, by first having a neural network roughly approximating it and then finding an analytic answer.
Thank you, that makes sense.
So maybe I can just add a comment or ask a question rather. So you're kind of trying to find these Calabi-Yau metrics, and you also are interested in dualities. Have you ever tried to try your algorithms on SYZ symmetries and finding some of the dual Calabi-Yau spaces? And if yes, what are the results? So can you?
Yeah, it's a very interesting question. I've not tried.
Yeah.
You want to see the T3 vibration directly in the metric.
Exactly. I mean, this is what people do, right? I mean, sometimes you want to find a dual to the one vibration, and you actually can't find the dual to that picture. Actually, I think Stu Chung Lau is in here. He's an expert in this, but you kind of find the dual Calabi-Yau by finding the dual metric of that Calabi-Yau using whatever methodology. So I think this is very fit for your algorithm. Probably you can investigate.
Thank you.
Excellent. Well, with that, since we're 15 minutes over also, and there were many questions, let's conclude. Let's thank Sven one more time. Sven, that was a wonderful colloquium. We thank you so much for coming and telling us about many aspects of your work, and we're looking forward to hearing from you and seeing your work in the future. Thanks a lot.
Thank you.
Thank you.